So Mingyue Tang is visiting us from the University of Hawaii. She completed her undergraduate studies at Nanjing University of Information Science and Technology in China. And she's currently a PhD student at the University of Hawaii in Mānoa, specializing in atmospheric sciences. Her doctoral research focuses on convective organization and propagation in the Madden-Julian Oscillation. That's basically this talk. Collaborating with Professor Giuseppe Torri, and she employs high-resolution cloud-resolving models and utilizes the Lagrangian particle dispersion model, LPDM, nested within SAM, which is a LES-type model, and the CM1 models. Currently, Mingyue is engaged in a 3-month visit through the ASP Graduate Visitor Program at NCAR, extending her stay until July 31st. And she's collaborating with me and Shanghai Liu while visiting this time. And we're investigating the convective offshore propagation in the tropical maritime continent, especially New Guinea, in this visit. So that's different from what she's going to talk about today. I think that's all there is. So ready for you to go. Thanks.
Role of copools in modulating convective organization during the Madden-Julian Oscillation. First, I acknowledge my collaborators. Giuseppe Torri, who is also my advisor, and Naoko Sakida. Before starting, I would like to introduce myself more. I'm a PhD student from University of Hawaii. Living in beautiful Hawaii, I love hiking in the early morning and watch the sunrise from the sea level, coloring the cumulus cloud and connecting the sky to the ocean. Besides the ocean views in Hawaii, I also enjoy the mountain views in Boulder, which is 3,000 miles away. Starting my PhD program at the onset of pandemic, my first trip out of Hawaiian Island was to Colorado. Before beginning my research presentation, I would like to acknowledge all the hosts, Bill Ko, Jimmy Duhia, and Shanghai Liu, and also ASP team for introducing me to NCAR, and for supporting my visit 3 times over the past 3 years. This year, I'm so excited to revisit MQ Lab, see a lot of familiar faces, and share my recent work here. This work mostly focused on understanding tropical convective organization using advanced numerical simulations. We will go through the details very soon. This video shows a 1-hour simulation from the cloud resolving model SAM, System of Atmospheric Modeling. The horizontal grid spacing here is 250 meters, which can resolve the cloud well. Even though it shows only 1 hour, we can still see evolution and generations of clouds. We can see the individual convective clouds initiate from the bottom and develop into deep convective clouds, propagate to the periodic boundaries on the other side, and finally decay as high-level stratiform. A simple question here, are the convective organized or not? And the simple answer is yes, because obviously the clouds are not randomly distributed in space. So the convective clouds are often organized and may let the convective system live for much longer time. So how can we quantify convective organization, and how can we understand this organized pattern? We want to answer them in my research. To set the stage, I will introduce the definition of convective organization here. The definition here may be a little different from traditional score lines in the mid-latitude. Nowadays, we also care about the organized pattern of mesoscale convective systems in different places, clustering of shallow cumuli, and self-aggregation, and also their impact on climate. So here I would like to give the definition. The convective clouds are organized if they are spatially or temporally correlated to the other clouds. However, the clouds themselves cannot directly interact with each other, but other mechanisms can help build the bridge. We usually think the radiative feedbacks, copools, and gravity waves can help us build this bridge to help organize the convection. For this work, for the smaller scale we care about, and also the model limitation with periodic boundaries, here we dampen all the gravity wave reflection and only study the role of copools in modulating convective organization. So what are the copools? Why are they so important for convective organization? To start with the precipitating cloud, when the rain droplet drop out of the cloud base, they will enter a very dry and very unsaturated environment. And then they will evaporate quickly. So this will drive a very strong evaporative cooling below the cloud base. And this will build a pool of cold, dense, and dry air. They will sink and spread out along the surface. Because the air pressure inside of the cold pool is higher than the environment, so we will have strong pressure gradients at the edges of cold pool to lift the cumulus upward to become a new convective cell. This is what we call dynamical forcing, and also well known as RKW theory. And I would say that RKW theory was the first paper introduced me to cold pools. I have a little complicated feeling right now present RKW theory here. So next I will share some of my very personal understanding of RKW theory. RKW theory mainly explains why the mid-latitude score lines can persist for several days. It emphasized the role of low-level wind shear that can build a vorticity balance with the cold front, so cold pool, so they can build very strong updraft at the front. However, in some specific environments, like for example in the tropics, achieving such strong low-level wind shear seems very hard. And also in the tropics, we have abundant moisture below the cloud base. So the environmental below the cloud base may not be so dry or so unsaturated as in the mid-latitude. But luckily, we have a lot of moisture in the tropics. So besides of the dynamical forcing, there is another argument that the cold pools can generate new convective cells by thermodynamical forcing. We also call it the Mohs ring theory. That means when we have this kind of density current, it's going to recover their neutral buoyancy. Even a little more moisture anomalies can build a sudden increase of moistatic energy around the edges of cold pools. So the parcels there has more thermal advantages to become new convective cells. Both these two ways can close this loop to show that the cold pools can generate new convective cells at the edges to help organize the convection. However, it's still too hard to find the evidence that cold pools really plays this kind of important role in some realities, especially in the tropics. That is why our research mostly focuses on the tropics. So from a formal statement, tropical convection usually has weaker updrafts, weaker downdrafts, weaker cold pools, and weaker low-level wind shear. So it was thought to be less organized or not organized. But when we look at the real satellite image here, we will see that in the reality, tropical clouds are organized over various scales, and it even can cover a very large areas. So why are they so organized? Do the cold pools still play a critical role in the tropics? I think they are both very open questions. So you may also ask if this figure is just a coincidence. I would say no. In fact, this huge organized cloud envelope occurs periodically over this warm pool region with very high sea surface temperatures from Central Indian Ocean to Central Pacific. It usually covers a huge area of roughly 1,500 kilometers in latitude and 4,500 kilometers in longitude, even larger than some of the mesoscale convective system in the mid-latitude. So this is commonly acknowledged as the Madden-Julian Oscillation. The Madden-Julian Oscillation, MJO, is a famous tropical planetary scale phenomenon that can influence the global weather and climate, like ENSO. But it is far less understood than ENSO. It has very special intra-seasonal timescale between 30 to 90 days. It usually behaves as a huge cloud envelope, initiates from the Central Indian Ocean, and then propagate eastward. Sometimes it will be killed by the maritime continent, but sometimes it can propagate through the maritime continent and reach the Central Pacific. For our study, we focus on the DYNAMO field. It locates at where MJO initiates and first develops around the Central Indian Ocean. The convection there has been assumed to play an important role as the self-induction mechanism to help MJO initiation. And here I would like to talk a little bit more about MJO. The MJO is not just fascinating for studying how the convective cloud get organized. It also has many open questions and debates. Nowadays, we have many different theories about how the MJO propagate eastward, how it initiates periodically, and how the maritime continent affected. All these ideas rely on key assumptions about how convective organization works. Therefore, studying small-scale cold pools and mesoscale convective organization still has critical implications for understanding large-scale MJO to improve our global subseasonal to seasonal forecast. In general, the overall goal of my research is to answer what are the physical processes that drive the development and organization of convective clouds during the MJO over the open tropical ocean. And then I will divide it into two. First, how does convective organization evolve during MJO life cycle? And second, how do cold pools modulate convective organization during the MJO? To answer these questions, we build a hierarchy of models to connect different scales and to capture the behavior of convective organization. The main model we use here is SAM, System of Atmospheric Modeling. It is a very idealized cloud-resolving model. So we force the model with the observational data from DYNAMO, and especially with the large-scale tendencies, so we can simulate the whole 3 months. Here, the grid spacing is 1 kilometer. And then we use WRF as the realistic simulation to validate the idealized simulation. We simulate the same period as 3 months, and the grid spacing here is also 3 kilometers. And at last, we want to investigate the physical mechanisms. So here we apply a new advanced model called the Lagrangian Particle Dispersion Model, LPDM, to run along with SAM. For the cost of computing time, here we only simulate 3 episodes. Each rainfall episode inside of MJO lasts for 2 days. So here we simulate 3 two-day rainfall episodes in the suppressed, growing, and enhanced phases of the first MJO event. We release 1,080 particles per column. The grid spacing here is 250 meters. The next question you may ask is, how can we diagnose MJO, this kind of large-scale phenomenon, with so small domain? So here I will introduce a local MJO index. This is a little different from the large-scale MJO index. So firstly, we apply the 30-day low-pass filter to focus on the subseasonal timescale. The x-axis here is the outgoing long-wave radiation, and the y-axis is the tendency. The colors here shows the dates evolve from the beginning of October to the end of December. We can see at first we have very significant 2 circles, and the third one is a little small. So we divide the coordinates into 8 phases. So here, phase 5 means we have minimum outgoing long-wave radiation and the tendency equals to 0. That means we have local convectively enhanced MJO phase. And phase 1 means opposite, the suppressed phase. So the key point here is we want to focus on the small-scale evolution of cloud themselves while keeping the focus on the subseasonal timescale. Later, we use different methods to validate the simulation. Here, I just show part of it. Here are the computed local phases from observational station and WRF. The x-axis here is the time steps. The time step here is 3 hours. And the y-axis is the computed MJO local phases. The black, blue, and red lines represent the observational station, WRF, and SAM respectively. So we can see clearly in the first 2 cycles, MJO is reproduced very well by SAM. The third one is a little tricky, so my further analysis will only focus on the first MJO events. And next, we want to quantify the convective organization. And I may ask this question at first, how should we quantify the convective organization. In fact, this is also a popular research topic in the recent 10 years. And now we have more than 10 kinds of indices to quantify convective organization. They're based on different assumptions. So when we have a more organized convection, some indices emphasize we should have decreased number of convective clusters. This is widely used in some popular indices like SKY, especially for studying self-aggregation. But the MJO case is more complicated. And other indices also emphasize increased cluster area and decreased distances between the clusters, also the non-random distribution of convective clusters. For the interest of time, I won't go through all the details of all the indices. And here I just show a popular index I work, which is designed for the organization of deep convective clouds. The key point of iWork is to compare the nearest neighbor distances between the centroids of convective clusters with randomly distributed points. Like the figures show here, the x-axis is the cumulative density function of the distances between randomly distributed points, and y-axis is the CDF of distances between actual points. The actual points are the centroids of convective clusters. And we compute the gray area below the curve. So we can assume if we have totally randomly distributed points, the area here is 0.5. That is the value of iWork. So once we have higher value of iWork closer to 1, that means we have more aggregated stage. Our hypothesis here is that the convective clouds are more organized during the MJO enhanced phase. So here are the results of iWork. The x-axis is MJO local phases, and y-axis is the value of iWork, also precipitating rates colored in blue, iWork colored in yellow, and also the number of convective clusters. So phase 5 is the center of MJO local enhanced phase. We can see generally this is very consistent with our hypothesis that we have more organized convective clouds in the enhanced phase. And also, we observe a very interesting phenomenon that, in fact, the 3 variables peak at different times. Firstly, the number of clusters peaks at phase 4, and then precipitating rates peaks between phase 4 to 5, and then last, iWork peaks at phase 6. We compare it with the most recent observational study using radar and also find this very consistent lagging time between the precipitating rates and the convective organization. We will say that this lagging time is crucial for MJO because it shows that the cloud can act as a local self-maintaining mechanism to prolong the convective active phase. Thus can help MJO's initiation and increase MJO's timescale. Besides, because MJO is an eastward propagating system, so this kind of local maintaining system can also increase the spatial scale of MJO. And here I will emphasize iWork only use the nearest neighbor distances between the clouds. And we want to find beyond the nearest neighbor distances, what can we find using distances? Let's take a closer look at how the network of distances changes in different phases of MJO. The x-axis here is the order of neighbor distances. 0 means the nearest neighbor distances using iWork, and order 1 means the next 2 nearest neighbor distances. Order 2 means the next 2 next nearest neighbor distances. The y-axis is the actual distances. So here we care about the difference between the enhanced phase and the suppressed phase, represented by the average of phase 5 and 6 minus the average of phase 1 and 2. The colors here represent the differences between those cumulative density functions. And the red line here represents the steeper distribution for shorter distances, which is what we're supposed to have for every column. Besides, we're also supposed to get a wider shadow of blue above the red. When we look at order 1, that is the nearest neighbor distances, we will find that, in fact, this column is not very consistent with our hypothesis, especially it have dark blue below the red here. So we suppose it is because the nearest neighbor distances is affected by the size of the updraft clusters. I won't go through the results of the size of clusters here, but I would say it's also an interesting question that the width of updraft also change a lot in different MJO phases. And a more important conclusion here is we find, in fact, if we have a higher order or larger actual distances of neighbor distances, in fact, it can show more robust organization in the MJO enhanced phases than order 0, that means the nearest neighbor distances. So maybe I work using just nearest neighbor distances lost some key information. And next, I want to take a step back and find the simplest but the most effective way to quantify the organization of convective clouds. And here, I also use the key concepts, distances, but here I care about the distribution of all the distances between all the clouds, rather than only the nearest neighbor distances. The x-axis here is the distances between the clusters or the points, and the y-axis is their probability. Different colors represent, colors in red and blue represent different phases, and black represent the randomly distributed points. So from mathematical perspective, for randomly distributed points, the distance and the distances and their probabilities should be linearly proportional if we ignore the effect of periodic boundaries. And next, how can we get a more aggregated stage? Here I determined that compared with the randomly distributed points as the black line here, we should have more short distances and less long distances. That means we squeeze the point together. In this case, we will have a more aggregated stage. So in this figure, it should have for the short distances, we may have the curve depart from this black straight line. That means we have a more aggregated stage. And if we look at different phases, we will also see this very robust, and even more robust than I work, is that in phase 6, we have a very significant departure from the straight line here. That means in phase 6, we have the most aggregated stage. However, a little different is that this range of distances, in fact, is really large. So we conclude that the more aggregated stage is organized by considerable distances between 20 to 45 kilometers in phase 6, rather than the nearest neighbor distances considered in I work. And we assume it is because of the large copools during MJO to cause these considerable preferred distances between clouds. And before going to the results of copools, let's review our hypothesis. This figure, in fact, is in another paper showing the most rings. The colors represents the surface-specific humidity, and this one is studies the radiative convective equilibrium. That means the no large-scale forcing in the tropics. So here we can see clearly we have positive moisture anomaly around the copools, mature copools. And the most ring theory based on the fact that the specific humidity appears with very different coefficients in buoyancy and moistatic energy. The coefficient in moistatic energy is far larger than the coefficient in buoyancy. So we can imagine when the gust front, when the density current is going to recover its neutral buoyancy, it's very possible that it can drive a very high value of moistatic energy ring around it. So here we assume this is the crucial mechanism that the most rings provide the thermodynamic advantage for new convective cells generation. And we'll also say the mechanical lifting is still important to work together with the most rings. For the following study, I wouldn't distinguish and quantify different roles of these two forcings. And our important hypothesis here, in fact, is the mechanical and thermodynamical forcing generate new convective cells at the same location. That is where most rings generated at the edges of cold pools. And also here I list some of the problems of studying cold pools. In fact, defining cold pools is really hard. And here I show some of the previous methods. So firstly, when people use observational station, they usually determine a sudden drop in temperature and moisture is cold pool. However, in fact, we don't know whether it is caused by the precipitating downdraft or not. And also, we don't know whether it actually have the spatial structure as the cold pool. Also, people use the modeling output to track the cold pool by clustering the dry, cooled patches. However, it really needs a very high time frequency of modeling output, and also recent work pointing out that the gray spacing should be smaller than 100 meters. Also, some people use traditional sensitivity experiment trying to test the role of cold pools. That is to turn off the evaporative cooling. But it may cause severe problems over the warm tropical ocean because turning off evaporative cooling not only removes the cold pools, but also removes the cooling. So it may lead to the conclusion that cold pools are harmful for convective organization. So in conclusion, the evolution of various properties make it difficult to separate cold pools, define their sizes, and find their role in organizing tropical convection. So we need a new method. And here is our new method, tracking the cold pool by the Lagrangian particles. The first step is to color the cold pool cores as the precipitating downdraft. Different cold pool cores or different downdrafts are colored by different IDs with four-dimensional contiguous gray boxes. It's noted that we also track them along temporal axis. And for the Lagrangian particle dispersion model itself, we initialize particles everywhere at the beginning. But then we only track the particles once enter the core and maintain the negative buoyancy as the density current originates from the precipitating downdraft. So, and then we can see the particles play a role in transferring IDs from downdraft to the cold pools. And more importantly, they have memory. So we can track the whole dispersal process, and each particle in the particles carries the IDs from the downdraft. A clock that can accumulate the time it maintains the negative buoyancy and also remembers the horizontal travel distance from the initial position it enters the downdraft. And also in the reality, we met some background wind. Luckily, in this case, the background wind is not as large as the gust front. So when we look at output, we can see the cold pool still maintains very good circle shape, but only a little affected by the background wind. So here we computed the horizontal travel distances adjusted for background wind advection. And at last, the particles modes of clock and horizontal travel distances, the mode of it then become the age and radius of the cold pools respectively. This is the method. And also here I list some of the advantages of using this kind of tracking compared to previous methods. So firstly, this method is very intuitive because the particles should follow the downdrafts. And second, the particles can be followed as the entire dispersal process throughout the cold pool's life cycle. And most importantly, all the information is carried by the particles, so it is unaffected by the collision between the cold pools or the dry cooled area falling apart. And next, I will show the results of the corpus by tracking Lagrangian particles. The x-axis here is the age of corpus, and y-axis is the radius. Different colors here represent different IDs of corpus. Here are 3 rainfall episodes. Each one lasts for 2 days in the suppressed, growing, and enhanced phases of the first MJO events. We can see the corpus features are very different in different episodes. So in the suppressed phases, the corpus only propagate in the first 2 hours and then stop propagating. However, in the enhanced phases, it can continue growing up and can even reach the radius as 60 kilometers. And later on, we want to look at the more detailed thermodynamical feature of the corpus. So here, the x-axis is still the age of corpus, and y-axis is the radius of corpus. The colors here represent the surface-specific humidity anomalies. We can see, especially in the enhanced phase, we have very strong, significant mold strings here. And it happens between the age of corpus from 1 hour to 2.5 hours. And even in the suppressed phase, we can still observe some mold strings at the edges of mature corpus. So I hope you still remember our previous result of the preferred organized distances. Now, let's look at the mold string locations more carefully. So in the enhanced phases, the location of mold strings are exactly between 20 to 45 kilometers. That is exactly consistent with the most preferred distances, organized distances between the clouds in phase 6. And even in the suppressed phases, if we're comparing the blue lines here with the black line, we'll find the preferred distances are between 15 to 20 kilometers, which is also exactly the radius of mold strings in the suppressed phases. So we conclude that the mold string location around the corpus is consistent with the preferred organized distances between clouds in phases. And next, we want to understand why we have larger and later generated mold strings in the enhanced phases. The first slide shows 3 snapshots of latent heat fluxes in the suppressed, growing, enhanced phases. And more detailing in panel in figure D, we have PDFs of latent heat fluxes in different phases, and the blue, black, and red lines represents the suppressed, growing, and enhanced phases, respectively. Very significantly, in the suppressed phases, we have for higher environmental latent heat fluxes. So we conclude the high environmental latent heat fluxes can accelerate corpus dissipation by helping the parcels there to recover its neutral buoyancy. However, the latent heat fluxes cannot explain the differences between the growing and enhanced phases, and then we analyze the maximum size and duration of the downdrafts in different phases. This is the cumulative density functions of them, and we can see for a certain percentile, the enhanced phases represented in red has significant larger and long-lasting downdraft than the growing phase. So we suppose it is because the growing phase has smaller size and shorter duration of precipitating downdraft, so the corpus or the mold strings here is smaller than those in the enhanced phase. And then last, we can see in the enhanced phase we have bigger and long-lasting corpus, later but stronger mold strings. And also we observe asymmetric mode in all the phases, especially in the enhanced phases. That is because we have westerly background. So it can increase the wind speed and fluxes at the downwind side and decrease the fluxes at the upwind side. This asymmetric mode is also important because it can make the radius of corpus as the preferred distances between the clouds rather than its diameter. So these are here are the conclusions of this work. We highlight the distribution of distances between other clusters rather than only use the nearest neighboring clouds. And also, the peak of convective organization lags behind of the precipitating rate by 1 to 2 MJO phases, and this is robust across different metrics. The spatial pattern of organization in enhanced phases prefers a sizable distances between 20 to 45 kilometers. This is consistent with the locations of most rings around mature cold pools. And most rings are more extensive and last longer during MJO enhanced phases, possibly because the decreased environmental latent heat fluxes and stronger downdrafts. This work has some implications. So firstly, the moist rings at the edges of mature cold pools facilitate the formation of more convective cores, thus increasing the degree of convective organization and explaining why the moist ring length scale is similar to the preferred cloud distance. Also, the cold pools organize convective clouds over large distances rather than making them tightly connected. This aspect should be considered in the future work to improve indices for quantifying convective organization. And last, cold pools, which shows a possible upscale effect, should be better represented in climate model parameterizations, especially for simulating MJO. We also met a lot of challenges, and also I think there are very interesting open questions I hope to figure out in my future work. So firstly, we also observe very complicated relationship between different cold pools. We observe collisions, merging, and also entrainment. And I think it's also very difficult work, and I really hope to talk more if you have some ideas or comments on it. Also, we also want to study the role of gravity waves, but it needs a simulation with open boundaries. So my current work shifts a little bit to CM1 simulation. And also here I'm very interested in the role of fresh water from the precipitation insert to the oceanic mixed layer. And I guess it plays an interesting role in controlling the surface fluxes here. Also, during the MJO, the dynamical factors are very hard to separate from the thermal factors. We also need proper sensitivity experiments for the cold pools over the tropical ocean. And at last, the cross-scale study and two-way feedback about clouds are really needed to connect directly with large-scale MJO theories. And again, I'm a PhD student from University of Hawaii. The overall goal of my PhD work is trying to understand convective organization and propagation associated with the Madden-Julian Oscillation. And this is the presentation I have today is answer the first question: how do the cold pools modulate convective organization where MJO initiates? And then I shift a little bit to maritime continents and to study how do the cold pools and gravity waves control the offshore propagation over maritime continents. And then last, I want to answer how do the organization and propagation interact with each other. So thank you all for attending my presentation today, and thanks for any comments you might have. Thank you.
Okay, any questions? Peggy had one.
You've covered an impressive amount of territory here, and it's really fascinating to see it from this point of view. And I'm wondering, have you looked at some of the observational evidence for some of these things? It's the 50th anniversary of GATE this year, and we saw some review talks at the American Meteorological Society meeting talking about all the field programs all over the tropical oceans. And a lot of the things that you're talking about based on modeling had come out, and I've seen them personally flying on aircraft, like the moist ring, that any cold pool boundary expanding, whether it's a strong storm or a little weak storm, you get the whole boundary layer lifted up, and you can actually see the boundary layer turned up on its side, and as you approach the storm, the moisture gets higher and higher and higher. Very impressive stuff. And talking about the fact that RKW doesn't work very much in the tropics and GATE, I think we had like maybe 5% of the convection in the Eastern Atlantic, was had deep cold pools, and the rest of it had little tiny cold pools, which we detected using theta E, and that worked pretty well. And one final thing, there was a professor at University of Hawaii named Gary Barnes who did a lot of work on the maintenance and scales of cold pools in different conditions using tethered balloon data in GATE.
Thank you a lot for your comments. And I feel observational study is still, I'm not very familiar with observational study here, and I can say something about some of the observational study compared with these results. So we also have a collaborator, Naoko Sakida from University of Oklahoma, and I would say the conclusion, in fact, especially about the lagging time, in fact, is very consistent. Even though we don't, I don't know how to use observation to study the 12th of the boundary layer, I feel it's very fascinating. And so up to here, the comparison with observations are very well. And now I can also have another paper to detect the cold pools. I feel it's also very interesting, but because we use different method, so the size of the cold pools are a little different from the results. That is maybe some limitation of, it's very hard to use observational study, especially radar or something, to see the cold pools. This is,
Yeah, you point out that the cold pools evolve a lot, which they do because of large fluxes, and usually the winds are stronger there. So at some point, the cold pool layer is no longer cold pool layer anymore because it's recovered.
Oh, yeah, thank you a lot for your comment. Yeah, I should learn more about observational study about cold pools. Yeah.
There's an online question from Chefeng. Great talk. Can you elaborate on why latent heat fluxes were suppressed during the MJO enhanced phase?
Yeah, thank you. I think this is a very, very interesting question. And in fact, I really like that paragraph I wrote at first in the paper. But I will say I will go back to the challenges I mentioned here. So I think this goes to another question: what controls the sea surface temperatures during MJO? So in general speaking, during MJO, we should have higher surface fluxes during the enhanced phase. This is larger timescale, mostly because the mechanism to controls the sea surface temperature are mostly from winds, and the winds are very important inside of MJO, and also some clouds can block the solar radiation to cool the sea surface temperature. However, in the smaller scale, we care here because we have 2-day episode inside of MJO. So for this kind of 2 days, maybe the primary mechanism to control the sea surface temperature is the fresh water from the precipitation. But I cannot prove it because this model doesn't have oceanic mixed layer, and I cannot prove how long the freshwater can stay in the oceanic mixed layer. So I think this is a very open question, and I really like this question, but it's really hard to prove. Yeah.
Thank you. Great talk. How different are the winds among the surface wind generally among the different phases of MJO?
I would say the situation is also a little complicated because here we have westerly wind burst. So the westerly wind burst timescale is larger than the convection, than the 2-day episode, but is smaller than the different phases of MJO. And also the mechanisms for westerly wind burst is still very, very open question. So from the results here, I would say the background wind in the enhanced phase, in fact, is comparable. It's a little larger, but comparable to the suppressed phases. So it's not too large difference. For the growing phase, for the episode in the growing phase we chose here, in fact, the wind speed is a little lower. So I don't know the specific answer for that, but I still think it's very open question. Yeah.
Okay, I think we exhausted the audience. Thank you again for your talk, and Mingyue is here until the end of July. Her office is close to mine on the 3rd floor, west side. If you want to discuss any of this in more detail, or her current work, which is on also on convection related to the land breeze and sea breeze. All right, thank you.